Hey everyone, so in this video we're going to be talking about the normal distribution, the empirical rule, and Chebyshev's rule. So before we move any further, it might be helpful to talk about the difference between parameters and statistics. Because understanding this difference gets you accustomed to the big picture of statistical inference in the first place. Basically, what we're doing is we're gathering some information from what's known as a sample, and we're making inferences about the larger population which we wish to know about. So parameters are fixed numbers that describe or summarize a population. And this is what's usually unknown, and this is what we're trying to estimate in the first place. So examples of parameters might be the population mean, which we usually denote by this Greek letter mu, or the population standard deviation, which we usually denote by this Greek letter sigma. Now, statistics are numbers that describe or summarize a sample. And examples of statistics might be the sample mean, which we denote by x bar. Remember, we walked through how to calculate a sample mean. And the sample standard deviation, which we denote by s. So the main difference between parameters and statistics is that statistics are not going to be fixed. And this is because we obtain a different number for the same statistic each time we take a new sample. So the sample mean using one sample of 10 people is going to be different from the sample mean using a different sample of 10 people. So each time you take a different sample, you're going to be getting a different sample mean. And so statistics are never going to be the same. Whereas parameters are going to be fixed numbers. They're not going to change no matter what sample we take. A couple other things to note here. We generally use Greek letters to represent parameters, and we usually use English letters to represent statistics. Now, this isn't always the case, but for the most part, it holds pretty well. So mu and sigma up here are going to be parameters, and x bar and s are going to be statistics. And the other thing to note down here is that an easy way to remember the difference between parameters and statistics is that population and parameter both start with the letter P, and sample and statistic both start with the letter S. So now let's talk about what's called a normal distribution. So we often work with distributions that are unimodal and symmetric, and the most common and most useful distribution that has these properties is called a normal distribution. So a normal distribution has two parameters. It has the mean, mu, and it has the variance, sigma squared. And the mean just tells us where the center of the distribution is. Where is this distribution located? And the variance tells us how spread out the distribution is, or how wide the distribution is. And we saw an example of this when we were calculating the sample variance a couple videos ago. So now let's talk about the empirical rule. So the empirical rule says that as long as the distribution is normal, then approximately 68% of values lie within one standard deviation of the mean, approximately 95% of the values lie within two standard deviations of the mean, and approximately 99.7% of values lie within three standard deviations of the mean. And this is a very handy rule because it gives us a quick way to make approximations without having to do any rigorous calculations, as long as we're dealing with values that are 1, 2, or 3 standard deviations away from the mean in a normal distribution. So the big drawback of the empirical rule, though, is that it only works when the values are exactly 1, 2, or 3 standard deviations away from the mean. So for example, if we wanted some information about values that are 1.5 standard deviations away from the mean, the empirical rule wouldn't be very useful for us. So here is an image of what the empirical rule kind of looks like. So we have the center of our distribution, mu, and remember the empirical rule says that 68% of the observations are within one standard deviation of the mean. So what that says mathematically is Mu minus sigma is one standard deviation below the mean, and mu plus sigma is one standard deviation above the mean. Similarly, the empirical rule says 95% of the observations are within two standard deviations of the mean. So we know that mu minus 2 sigma, or two standard deviations below the mean, and mu plus sigma, or two standard deviations above the mean, the interval between those two values is going to contain roughly 95% of the observations. And then the same thing goes with three standard deviations below the mean and three standard deviations above the mean. The interval between there contains 99.7% of the observations, approximately. So let's look at an example. IQ scores follow a normal distribution with a mean of 100 and a variance of 225. So before we go any further, we should notice that this is given to us in terms of a variance, and the empirical rule works best when we have this in the form of a standard deviation. So before we do anything else, let's figure out what the standard deviation is. And remember, the standard deviation is just the positive square root of the variance. So to find the standard deviation, we just take the square root of the variance. So that's the square root of 225, and that's going to be 15. So our standard deviation, or sigma, is going to be 15. And then we could just look at each of these pieces right here, and we can plug our information into these spots. And then we'll be able to fill in each of these spots right here with actual numbers. And it'll give us a lot of useful information in one picture. One standard deviation below the mean is going to be mu minus sigma. And remember, mu was 100 and sigma was 15. So one standard deviation below the mean is going to be 100 minus 15, or 85. Similarly, two standard deviations below the mean is going to be mu minus 2 times sigma. So that's going to be 100 minus 2 times 15, or 70. And we could keep doing this with each of these values, and we would come up with all of this information right here. And what we can do is we can take this picture right here, and we can fill in each of those pieces. And if we do that, we'll end up with something like this. So remember, the mean was 100, the mean IQ score was 100, and one standard deviation below the mean, remember we calculated, that was 85. So that's where this piece goes right here. And then we did the same thing with 70 and with 55. And we filled in all these numbers, and now we have a lot of really useful information in this one image. The other thing to pay attention to here is that each of these gaps here, from 70 to 85 or 85 to 100, each of those gaps is one standard deviation. So 100 to 115, that's a distance of 15. And remember, our standard deviation was 15. So each time you make this jump to this next number, you're moving one standard deviation away, which should make sense. So let's look at a couple examples of how we can use the empirical rule to make some quick approximations. So our first question here is, what percent of people have an IQ score between 85 and 115? And this is really easy because we already have 85 and 115 listed here. They're exactly one standard deviation away from the mean. So we know that approximately 68% of people have an IQ score between 85 and 115. So that one was easy. So what if we were to ask what percent of people have an IQ score above 130? Now, this isn't quite as easy. I mean, we have the number 130 listed here, but we don't really have a quick number to look at to say, like, oh, yes, like this percent is above 130. But what we do know is that we're interested in whatever this tail is right here. And we know that because we're interested in everything above 130. which is everything to the right of 130. So this vertical gray line right here, we're interested in everything to the right of that. So we can use the empirical rule and the information it gives us to find what that percentage is, approximately. So we can look at something like this. We know that 95% of the observations are going to be between 70 and 130. So what's left to make this an even 100% is 5%. If 95% is between 70 and 130, then the rest is 5%. And since this distribution is symmetric, we can take that 5% that's left over and divide it by 2. So that way we can find what's in each tail of the distribution. So in other words, we have 2.5% in the left tail and 2.5% in the right tail, and that makes up the remaining 5%. But what this does for us is now it tells us what's above 130. Now we know that approximately 2.5% of the observations are going to be above 130. So to answer the question, approximately 2.5% of people have an IQ score above 130. So let's look at a slightly more complicated example. What percentage of people have an IQ score between 70 and 115? Now we can use the same logic as before. We just have to break this up into smaller pieces. So remember before, 68% of the observations were between 85 and 115, and we can use this information because we need information regarding this number 115. And since we also need information regarding this number 70, we're going to have to use this information right here that tells us that 95% of the observations are between 70 and 130. And what we want is the area between 70 and 115, which is this area in yellow right here. And using the same logic as before, we could say like, oh, well, if this is 68%, then the rest is going to be 32%. And since the distribution is symmetric, just like before, we could split that 32% up into two 16% intervals right here. And then, just like before, we could take that 95% and say, well, 5% is left over. So there's going to be 2.5% over here and 2.5% over here. And what that does for us is it says, well, now we know 16% is above this interval, and we know that 2.5% is below this interval, and we know that the entire thing is 100%. So all we could do is take that 100% that represents this whole thing and subtract off the intervals that we don't want, and what we'll be left with is the interval that we do want. So what we could do is we could take this 100%, which represents the entire thing, and we can subtract off this 16% because we don't want this 16% right here. And then we also don't want this 2.5%. So we can subtract this off as well. And what we'll be left with is 81.5%. So to answer the question, roughly 81.5% of people have an IQ score between 70 and 115. So we talked about how one of the major drawbacks of the empirical rule is that it only works when we're dealing with exactly one standard deviation away, or exactly two standard deviations away, or exactly three standard deviations away. And the other major drawback of the empirical rule is that it only works when we're dealing with a normal distribution. So if it's not unimodal and symmetric and it doesn't have that shape, then we can't use the empirical rule at all. And this is where Chebyshev's rule comes in. And Chebyshev's rule says that for k greater than 1, at least 100 times 1 minus 1 over k squared percent of the values lie within k standard deviations of the mean, regardless of the shape of the distribution. So this is the way we correct for that strict condition that the empirical rule has that says it has to be a normal distribution. So what Chebyshev's rule does is it provides a lower bound for the percentage of the values within a certain number of standard deviations of the mean. And what the empirical rule does is it gives us some really nice approximations when the distribution is normal. So since Chebyshev's rule relaxes the really strict condition that the distribution has to be normal, we're always going to end up with a lower percentage using Chebyshev's rule than we will by doing the exact same calculation using the empirical rule. So let's look at an example. So suppose the mean height for adult males is 70 inches with a variance of 9 inches. So without assuming anything about the distribution, that's the important part here, what percent of males are between 64 inches and 76 inches tall? So just like before, we were given a variance. So if we're given a variance, we should probably, just to be safe, convert it into a standard deviation so that it's a little bit easier to work with. So remember, all we need to do is take the positive square root of this variance. So the square root of the variance is going to be the square root of 9, which is going to be 3. So our standard deviation is going to be 3. Now, since we can't assume anything about the shape of the distribution, we don't know for sure if it's normal. And if we don't know it's normal, then we can't use the empirical rule to help us here. And what's even worse is that we can't even draw a picture to help us out. But what we can use is Chebyshev's rule, because Chebyshev's rule says that regardless of the shape of the distribution, we can still come up with a lower bound for whatever approximation we're interested in. So remember that Chebyshev's rule says that for k greater than 1, at least this much percent of values lie within k standard deviations of the mean. So we need to figure out what k is. So in other words, we need to figure out how many standard deviations 64 is away and how many standard deviations 76 is away from the mean. In other words, we need to solve for k in this interval right here. And the interval, which we were given, was 64 on the lower side and 76 on the higher side. So what we need to solve for is mu minus k sigma is equal to 64, and mu plus k sigma is equal to 76. And we already know that the mean is 70 and the standard deviation is 3. So what we're left with in these intervals is 70 minus k times 3 is equal to 64, and 70 plus k times 3 is equal to 76. And that's what we have down here. 70 minus k times 3 is 64. 70 plus k times 3 is 76. So if you solve for k in either of these equations, we get k equals 2. And all k is going to represent is the number of standard deviations away from the mean we are. So since k is equal to 2, these two values here are 2 standard deviations away from the mean. And this is useful information because now we can plug it into this formula right here. Now we know what k is here. We figured out that k is equal to 2. So when we plug this into the formula, we get 100 times 1 minus 1 over 2 squared, which is the same thing as 100 times 1 minus 1/4, which is the same thing as 100 times 3/4, and that's 75%. So what that means is at least 75% of males are between 64 and 76 inches tall. Now, one thing to note here about that example is that if we had used the empirical rule instead, we would have concluded that approximately 95% of males are between 64 and 76 inches tall. But instead, since we were not given any information about the distribution, we couldn't use the empirical rule, and instead we concluded that at least 75% of males are between 64 and 76 inches tall. So the difference here is that we're making approximations using the empirical rule, and with Chebyshev's rule, we're providing a lower bound. So let's look at some final takeaways from this. If we're told that the distribution of the data is normal, then we should use the empirical rule. And that's because the empirical rule was designed specifically to handle the normal distribution. It's designed specifically for those situations when we're interested in exactly one standard deviation away, or exactly two standard deviations away, or exactly three standard deviations away in a normal distribution. Now, if we're not told anything about the distribution or it's not known, then we should be using Chebyshev's rule for our estimations, because the best we could do there is to just provide a lower bound. And then the last thing here is that the empirical rule and Chebyshev's rule are applicable whether we're dealing with samples or populations. So in this case, we were dealing mostly with populations in these examples, but it works for samples also. So anyway, that's the end of this video. I hope you found it enjoyable and useful, and I will see you in the next video. Take care.